Alright, so we left off with this Hamiltonian. We call it the electronic Hamiltonian because it ignores the nuclear repulsion terms, but counts all the terms that would deal with an electron in a diatomic molecule. And so let's take a look at how we might go about calculating the energy of a bonding orbital for a particular diatomic molecule. We could begin with a simple version of the bonding orbital where the wave function of the bonding orbital is some combination of two functions, one of which comes from one atom and the other comes from the other. And these are the two functions that we assume are overlapping to make the bond. If we apply the electronic Hamiltonian to those functions, we get a situation that looks like this. Now we're assuming, the way that we've written this, that the functions themselves are not optimized. Are not normalized. And so we can write a expectation value for electronic energy, which we'll denote with this epsilon, as the Hamiltonian, the electronic Hamiltonian, applied to the wave function, multiplied by the complex conjugate of that wave function, integrated over all space. And here's our wave function. So there's our setup. Now we could simplify this a little bit by, I don't know if I'd call it simplify it, but begin the math by applying this operator into these parentheses. So we end up with the Hamiltonian applied to this wave function, Hamiltonian applied to this wave function. And then we go ahead and FOIL the top part. And so when we do that, we're going to end up with a CA times CA portion, CB times CB portion, so that's here, and then an A portion times B, B times A. So that's what we get right here. And so we've still got the Hamiltonian in each case applied to the wave function and complex conjugate out in front. And so the question that comes up is, this is starting to look a little bit complicated. Do things get easier from this? Well, even if we haven't normalized this overall wave function, we can assume hopefully that A and B are normalized. If that's the case, then this integral is 1 and this integral is 1. So these two terms become just the square of these coefficients. Let's look for anything else that might be easy. There's nothing on the top that's going to drop out for us easily that I can see. But this looks to us like it might drop out because it is the integral over all space of one wave function times another, times a different one. So we might think from an orthogonality standpoint that these will drop out. But they don't have to be orthogonal to one another because they're not on the same atom. And so this is going to have a value between 0 and 1 that's going to relate to how much the orbitals overlap with one another. If this is an anti-bonding orbital and the orbitals don't overlap at all, then this term is going to be 0. If these orbitals overlap very, very significantly, then the overlap integral is going to be larger and could begin to approach 1. We've gone ahead and named each of these terms as well. These are our expectation values. So this is an energy term related to just the A orbitals, an energy term related to just the B orbitals, and then an energy term that's related to A and B. And if we had the mathematical form of the orbitals written in here, we or a computer could go ahead and evaluate the values of all of these integrals. And then once we have those, we can find appropriate values for A and B that would give the lowest energy by the variational method. So that's what a computer would be doing in calculating the electronic energy of a diatomic molecule. Next slide gives us a little bit more of a picture of what we mean by the overlap integral. Again, it's just, it looks like it would be 0, and if these were orthogonal to one another, it would be, but orbitals on separate atoms don't have to be orthogonal to one another. So we're looking at an overlap that is 0 in this case, non-zero in this case. I mentioned earlier, if we knew the values of these integrals, we could go ahead and find the values of CA and CB. And we're going to take a look at how that would happen on the next few slides. We begin again with that equation, which we will just rearrange a little bit in a way that makes it a little bit more convenient for what we're about to do. So all I've done here basically is multiplied both sides by the denominator. And the question is, why would I do that? And the answer is because it makes it a little bit more convenient for what I'm about to do. We want to find the minimum energy, and we want to solve for the values of CA and CB to do that. And if we want to find the minimum energy, you were taught in your calculus classes that finding the minimum of a function means finding the first derivative and setting that derivative equal to 0. And so if we take the derivative with respect to CA and the derivative with respect to CB, and I'll ask you to believe me that this is a correctly taken derivative. Folks who want to practice that out on their own can, but I won't ask you, even in a regular semester, I wouldn't ask you to do that necessarily on a test. But if we take derivative of energy with respect to CA, we get an equation like this. We take the derivative of energy with respect to CB, we get an equation like this. And it looks complicated to solve, but remember, we're setting the derivative equal to 0. So if the derivative is equal to 0, these terms drop out. And we end up with just these terms and these terms. Same thing here. So we'll get a sample algebra on the next slide for how that would work. And we'll use this first one as our sample, but the second one would work the same way. Let's move me out of the way a little bit. So here's that same equation. We've taken a derivative of energy with respect to CA, and this whole term is going to drop out because we're setting the derivative equal to 0. And so now we have this equation to solve. Working through the algebra on it, we end up with this form just by distributing the energy into the parentheses. And then we end up here just by dividing both sides by 2. And then we subtract one side of the equation so that we get the whole thing set up as equal to 0. What we have here is referred to by quantum chemists and by quantum mechanics physicists folks as a secular equation. And we would get an analogous result by having started with the derivative with respect to CB. And I'm going to put both of those equations on the next slide. Here's one final form where we've factored CB out of these two terms and the CA out of these two terms. And so here's our two what we call secular equations. And so we've got simultaneous equations. It works out fairly well because we have two equations and two unknowns. Again, that's assuming that we can evaluate these integrals and know the energy. And this becomes a fairly simple item to deal with. In order for there to be a non-trivial, by non-trivial I mean, this equation would be satisfied if CA and CB were both 0. That's considered a trivial solution. But in order for us to have a non-trivial solution, the secular determinant that's generated by these has to be 0. And this is where I'm jumping into some math that you may not have seen before by referring to a determinant. Those of you that haven't taken linear algebra before won't necessarily know what this means, but if we make a determinant out of the coefficients, we're assuming CA and CB to be our variables. If we make a 2 by 2 matrix out of this is the top left term, this is bottom left, this is top right, this is bottom right. If we make that sort of a determinant and set that determinant equal to 0, it would look like this. The algebra here is not difficult to solve this determinant. It's long and it's boring, and so I'm not going to make up slides to do this. Again, if you really, really like algebra, you could work this out for yourselves. But what it comes down to is it's finding a determinant. So it's this term times this term minus this term times this term. So there's a lot of foiling to do and then gathering of like terms and so on. And what we end up with is what we have at the top of this next slide here, a equation for energy of the orbital, of the Hamiltonian that describes this bonding orbital. And it's all related to these integrals, the overlap integral, the energy with respect to the A orbital, the energy of the B orbital, and the AB energy. And all of these terms are just those integrals. It looks very, very complicated. It's not something, obviously, that I would ask you to do of your own accord, but it's something that computers can handle pretty well. On the other hand, if we're dealing with a homonuclear diatomic, so H2, F2, Cl2, whatever, then this is going to be equal to this, and we'll be able to combine a lot of terms. And the algebra would simplify quite a bit. And we'd end up, because of the square root here, with two possible energies, an E1 and an E2. Now something to remember is that HAA and HAB are both going to be negative, and the overlap integral is going to be positive and between 0 and 1. And so that means that E1 is going to be less than E2, or epsilon 1 is going to be less than epsilon 2. So E1 is the bonding orbital, and E2 is the anti-bonding orbital, or epsilon in this case. Now, if we substitute these, and you guys can try this on your own, we substitute these back into the secular equations, we're going to find that if we use E1, we get Ca equal to positive Cb, and if we use E2, we get Ca equal to negative Cb. And like I said, these are the bonding and the anti-bonding orbitals, and they come from adding and from subtracting the original atomic orbitals. And so what we end up with is exactly what we described in Gen Chem, if you got as far as MO diagrams, and in organic, where the bonding orbital is the result of two orbitals approaching at the same sign, and the anti-bonding is the result of two orbitals approaching with opposite sign. And the bonding wave function having significant overlap between the atoms, with a lot of electron density here between the atoms, and the anti-bonding wave function having no overlap between the atoms because of the destructive interference that's caused by them approaching positive to negative. And unfortunately, we're going to have to pick up with this topic on the next video, because we're going to run out of time before I can do this justice. But just pause your notes right here and pick up with the next video right away, and this is where we'll start.